Okay, guys, welcome back. Here I'm detailing the solution of homework 4, and I'm talking about question 1b. 1b, what is the question? The question was about finding the all possible matrices of this form that solve, so we have to find these missing items, that solves the following problem, where you do minimize on C and R, half of the A minus CRT on the known parts, known, and this is the L2 norm squared, okay, plus half of the Frobenius norm squared of C plus the Frobenius norm squared of R. Okay, so this is our problem. Okay, now of course, where it's given that CRT is of the following dimension, is 2, 1 multiplied by a 1, 2. So basically it should give you a 2, 2. Okay, so as you know, we've talked about this question a lot during the previous classes. So I'm defining here C to be equal to xy. So basically we'll be looking for the x and y. And to me, RT is equal to R. This is supposed to be R. RT is equal to ST. Okay. So if you do perform the product, the dot product CRT, should give you the following. You should have SX, TX, SY, and TY. Okay. So here we go. Now, what about this matrix A minus CR? So A minus CRT is going to be equal to the following. So it's going to be equal to, let's say, the star minus SX, 1 minus TX, okay? And here we get 3 minus SY, and finally, S star minus TY. Got it? Okay. So if you're planning to compute the norm on the known parts, okay, you don't have to use the whole norm. So the norm on the known parts of A minus CRT, known, okay, I'm talking about the L2 norm square, it's going to be supposedly the square root of the sum of what? Of these parts which are known, okay? Non-parts of A only. So basically, you're going to have half of, don't forget we do have half here. So it's going to be half of 1 minus TX squared. This is 1 minus TX squared. And half of 3 minus SY squared. And plus, well, now let's talk about the Frobenius norms. Here, well, we said this previously in the classes, that the Frobenius norm, in fact, of C is going to be x squared plus y squared. Okay, and similarly for R. I'll get back to it. Okay, so this is in fact the objective. Now, why is that happening? Because CCT, so this guy, in fact, is the Frobenius norm, sorry, should be like this. Frobenius norm squared of whom? Of C, and there is a half in front of it. And similarly for this case, okay? So to get this Frobenius norm, well, we got CCT, which is equal to, in fact, x squared xy, xy, y squared. And we got also CTC. CTC is more important because it's just a 1-1, so it's just a scalar, x squared plus y squared. So the common eigenvalues between CCT and CTC are only given by whom? By x squared plus y squared, okay? Which means this is the singular value, the unique singular value for C, okay? In 1 squared, and the Frobenius norm, what does it say? It's the square root of the sum of the singular values squared. So this is the eigenvalue there. Well, with the square and the square root, you get the following, that the Frobenius norm of C squared is going to be equal to the square root of x squared plus y squared, but squared, so which means you can remove the square. Okay, and similarly for whom? For R. Okay, so here we go. So now we are set, and we are ready to find the objective, the objective function solution, or for the normalization problem solution. Okay, so I'll move on to a new board. So now let's consider our previous objective as L and differentiate with respect to X. Okay, in that case, we'll get the following derivative. You're going to have minus t times 1 minus tx, because we had basically half of 1 minus t squared, minus tx squared, and plus what else? Plus you're going to have plus 2x plus plus x, because we have half of x squared. When you differentiate with respect to x, you get plus x. Similarly, the derivative with respect to y is going to be equal to minus s times 3 minus sy plus y. Now, we have also derivatives of the objective with respect to t, and you get the following. You get minus x times 1 minus tx plus t. Okay. And you get derivative of L with respect to s, and you are having minus y, 3 minus sy plus s. Okay. So let's call these, give names to these equations, 1, 2, 3, 4. So we can use them to extract some partial results. Okay. So basically, from 1, what can I get? From 1, I can get the following. I can get that x is in fact equal to, when the gradient is equal to 0, of course, all these partial derivatives should be equal to 0 if I'm looking for a minimum. Okay. So x should be equal to t times 1 minus tx. Okay. Which means that basically, if you work it a little bit, you get x times 1 plus t squared equals t. So this is x in terms of t. X is t over 1 plus t squared. Okay. Similarly, if you take 2, you're going to have the following. You're going to have y, which is equal to s times 3 minus sy, and it leads to y, which is equal to 3s minus s squared y. Basically, it means that y times 1 plus s squared is equal to 3s. So finally, y is equal to 3s over 1 plus s squared in terms of s. Okay, so these are partial results you can get. Okay, now you take these results and you plug them in 3 and 4. So you'll be able to get the values potentially of t and of whom of s. Okay, so let's start with 3. You plug them in 3. So in 3, you're going to have the following. You're going to have t, yes, times 1 plus t squared over 1 plus t squared all squared minus 1 plus t squared equal to 0. Can work it out, substitute this here. Okay, so you end up with what we are just writing. So basically, it leads up to the following, that 3 times t times 1 minus 1 plus t squared, 1 over 1 plus t squared, all squared equals 0. Okay, so basically there are 2 roads here. There are 2 roads. The road that says that t equals 0. Okay, and the road that says that 1 plus t squared is equal to 1. Is equal to 1. Okay. Okay, here we go. So if t is equal to 0, of course, it means that x is equal to 0. And we have two items already filled, one in R and one in C. And if 1 plus t squared, you consider the other option, is equal to plus or minus 1. There are 2 options here. Now we can consider that, well, t could be also a complex number. So if 1 plus t squared is equal to minus 1, then we do have t squared, which is equal to minus 2. And you have potentially 2 possible solutions for t. T is equal to plus or minus root of 2i. Okay. Well, if the other option is 1 plus t squared equals 1, and this brings you back t equals 0. Okay, so basically x equals 0. From that previous one, you get a value for x also. Okay, so x here would be equal to plus or minus root of 2i divided by whom? Well, 1 plus t squared, and in both cases, it's negative 1. So it ends up to the plus or minus root of 2i. Okay, so these are the potential values for x and t here. Okay. Okay, now let me take this result now with me, and I'll move it on to the next table. Now with the next table, what do I have? I have work on the fact that, well, y times 1 plus s squared was equal to 3s. So you get the following, that in fact, y times 1 plus 9y squared, plug it in 4 over 1 plus y squared equals 9y over 1 plus y squared. Okay. So if you work it a little bit, there are two options. The option that says, in fact, y equals 0. So s would be 0. Okay. Here, what did I do to get this? Well, I brought everything to the side and I wrote it this way. So let my answer be complete. Plus 9y times y minus 1 minus y squared, and all divided by 1 plus y squared. If you want to unify the denominator, once you bring this guy to the left side. Okay, and we divide by 1 plus y squared. This should be equal to 0. So from here, you get the option that the y could be 0, or the option that you can have here a 4th degree polynomial of y. So here, the second option is here. I'm going to say that we do have to solve y4 minus 9y cubed plus 11y squared minus 9y plus y equals plus 1, sorry, equals 0. Okay, and here there are two, in fact, there are 4 roots, 2 real ones and 2 complex ones. So I'll give you straight the 2 real ones. So it's 1 over 4 times 9 plus 3 root of 5 plus or minus square root of 110 okay. And the second pair is complex. You get the following. I'll let you know how I got these roots. Well, it's you can get it manually. It's quite easy, but I simply used Wolfram to solve my polynomial, and I got these analytical solution. Okay, we don't have to waste time there. Okay, so these are the 4 roots, which means once I got these, I can get what? I can get the values of t. Okay, that's it. So I'm almost set. So basically, I got the values inside C. We said that C is basically composed of whom? Composed of X and Y, and R is composed of S and T. So you substitute here, plug it in T, and you got the possible answers. One of them, of course, is to have T to 0. Okay, and you can check the second degree conditions if you want to look forward for the most complete way to solve your question. But I think it's pretty enough here. Well, this is it for question 1B.